Welcome to the GlobalFoundries Foundry Services online seminar. My name is Sean O'Kane from ChipEstimate.com. Today, we are pleased to introduce our three speakers from GlobalFoundries: Eelco Bergman, Vito Dai, and Charlie McDonald. Eelco Bergman is the Director of Product Marketing, responsible for GlobalFoundries' advanced interconnect offering, encompassing wafer bumping, 2.5D, 3D TSV, and Turnkey Services. Eelco has 30-plus years of semiconductor packaging experience with leading companies including Amkor Technology and Micron. Vito Dai is a PMTS DFM CAD Engineer at GlobalFoundries, where he is responsible for pattern-based and lithography model-based DFM. He was one of the co-inventors of the patented DRC Plus technology, which revolutionized physical verification using 2D pattern matching. He entered the field of DFM and OPC when he joined AMD in 2005, and he received his Ph.D. in electrical engineering at the University of California in Berkeley in 2008. And last but not least, Charlie McDonald is the Director of Product Marketing responsible for GlobalFoundries Test and Product Engineering Services. Charlie has 30-plus years of semiconductor industry experience with leading companies including LSI and NVIDIA. This will be a 30-minute seminar. You can also search for the GlobalFoundries IP catalog by simply going to ChipEstimate.com. So without any further ado, let's learn more about the Foundry services from GlobalFoundries.
Good afternoon. My name is Eelco Bergman, Director of Product Marketing for Advanced Interconnect at GlobalFoundries. Today we're going to provide you with an overview of a suite of services offered by GlobalFoundries. These services are designed to facilitate the collaborative design, engineering, and manufacturing and data sharing necessary to enable our Foundry 2.0 model. We'll cover each of the services listed on this slide with the exception of the prototype and MPW services, the schedules for which can be found on our Foundry View portal. Kicking off the session will be Vito Dai from our Technical Solutions team to talk about design and DFM services. Following Vito will be Charlie McDonald, who will cover our product and test engineering services, and then I'll close out with a discussion of our turnkey service offering.
Thank you, Eelco. I'm here to present on the design for manufacturing and design-enabled manufacturing services offered by GlobalFoundries. It's often known by the names DFM and DEM, respectively. So on this slide, you can see the portfolio of tools and services offered by GlobalFoundries. And these DFM solutions are here to enable first silicon success by our customers. The tool on the upper left-hand corner is called MAS, or Manufacturing Analysis and Scoring, and it is our rule-based DFM deck. This deck enables via doubling as well as other DFM enhancements and scores them to ensure compliance and design. The second set of tools, so-called model-based DFM hotspot identification and verification, refers to our model simulation capabilities. This is silicon-accurate silicon models used to simulate potential lithography hotspots during patterning so that they can be identified and eliminated from design. The third set of tools is the fill and CMP modeling. This is our planarity models for the chemical mechanical polishing process, and it identifies locations in design where the density of metal may not be sufficient to ensure planarity in the final manufacturing. The fourth set of tools is the DFM yield scoring, also called CAA or CFA analysis. This has to do with critical area analysis and helps to identify locations which are sensitive to random defects. And the last set of tools that is highlighted here, which I will go into more details for, is the DRC Plus pattern matching set of tools. We have pioneered the pattern matching technology as a fast alternative to doing simulation. It allows rapid identification of potential 2D yield detractors in design. And this has great implications on the design time cycle. So here we see the impact of DRC Plus in physical verification in the timing closure loop. On the left side is the traditional timing closure loop in the routing domain. First, you do timing enclosure, so you placement routing, timing analysis, and then you do ECO for timing enclosure. And then you enter a separate loop for physical verification, which includes DRC LVS, but also the DFM analysis and printability simulation. The issue here is that when the modifications during the physical verification is significant enough to affect timing, now you have to go back to the timing closure loop, and this has significant impact on the design cycle time. Using the pattern-based technology called DRC+, we are able to insert process information in the form of pattern-based checks inside the timing closure loop itself. So you see on the right that the DRC+ has been inserted in the timing closure loop. The result is that you can do all your physical verification and timing closures together within the same loop with very little impact in the overall tool runtime. And the final physical verification is just sort of a secondary verification to make sure that the DRC Plus deck has not missed anything. And this is, of course, the Foundry optimizes the DRC Plus deck in order to prevent such occurrences. So this allows you to more quickly close on design for both timing and physical verification. DRC Plus is a full chip physical verification solution. GlobalFoundries provides a rule library, which is an industry first silicon validated set of yield critical patterns. This pattern is then inserted into a complete suite of EDA tools, including Cadence Encounter, Cadence Virtuoso, and the Synopsys ICC ICV, as well as Mentor Caliber. So this GlobalFoundries offers a complete suite of support for industry standard tools. Also in the DFM portfolio is design-enabled manufacturing. This helps us use design information and design analysis in the fab to quickly identify yield detractors and feed that back into the design. For instance, in this case, the DRC Plus has been used to identify hotspot patterns within the design. On a separate identification step, the scan diagnosis software has been used to identify where a yield loss has happened, where a scan failure has happened. By intersecting these two results, we can identify a care area and localize where to apply metrology inspection, and also to fine-tune the defect scans in order to increase sensitivity to find small defects, tiny defects in fact, much smaller than the wavelength of light in the design, on the wafer. Okay. So you can see here the suite of tools that support this effort, including Synopsys, ICC ICV, Cadence Encounter, and Mentor Caliber, as well as the scan diagnosis tools that's used to do this correlation, which is Yield Explorer and Yield Insight. The tools that can accept this type of defect inspection data care area is the KLA Tenker nanopoint technology. So as you can see, we have a very strong portfolio of design-enabled manufacturing solutions in GlobalFoundries.
The product and test engineering functions within GlobalFoundries can provide many capabilities to our end customers. These capabilities not normally associated with Foundry services. They all fall under the umbrella of CDM, which we call Collaborative Device Manufacturing, which is unique to GlobalFoundries. These capabilities include product IP Skew analysis, new product introduction, yield engineering, and failure analysis with root cause diagnosis. Through our CDM model, we share all aspects of data in the yield learning phase of product bring up. Our open data sharing environment is geared at enabling customers to see all test and yield data to encourage a collaborative approach to yield ramp. Our internal production test capabilities are managed by experienced personnel who track yields, test time, develop and sustain hardware, perform yield dispositions and strive to improve efficiencies throughout the whole production process. Also, through our collaborative approach, we work closely with the customers to reduce cycle time by managing all logistics aspects of the production flow to ensure customer demand is met. Yield learning depends significantly on the ability to use design and test data to root cause defects. At GlobalFoundries, we collect test data at the bin and macro level to selectively drive root cause analysis. Scan and memory diagnostic solutions we employ allow us to quickly pinpoint failing nets or bit cells to drive to the physical location. Volume diagnosis is employed to allow us to analyze large data sets across all stages of test, which, through Yield Explorer, provides statistical analysis to determine failure trends not seen at single die or at wafer level basis. The importance of having design data to perform root cause analysis is paramount to yield learning. But we also know that access to design data is not an easy proposal in a foundry fabless environment. Foundries typically take on the task of failure analysis and corrective action for yield improvement. But fabless teams are not comfortable sharing sensitive data, particularly IP, for the purpose of yield enhancement. GlobalFoundries has worked with Synopsys to find a way out of this catch-22 situation. The key to this solution was to realize that the design data, which was necessary for yield analysis, is a different view of the design data that is considered sensitive. Once this was understood, Synopsys enabled a capability for extraction of only the yield-relevant information from design data, and by adding encryption to this data, finally making it secure, where it can be sent over to the foundry without any concern for disclosing critical IP. This means of moving such information between a fabless customer and GlobalFoundries is called a snapshot. In our model, the customer loads their data into Yield Explorer on their site, thus controlling the privacy of their data, and generate the diagnostic snapshot, which is then sent to GlobalFoundries. Once GlobalFoundries receives the snapshot into Yield Explorer on their site, root cause analysis can be realized. GlobalFoundries has developed a close relationship with PDF Solutions to enable a forward-looking approach to yield learning. Through internally developed characterization vehicles containing real product structures and IP, we can very quickly extract important data to drive DFM by shortening this feedback loop. This is achieved by generating large parametric data sets which are analyzed through the manufacturing process of the CVs. GlobalFoundries has seen 2 to 3x faster yield ramps using this process compared to industry standards. An example of how our feed-forward yield learning improves NPI product yield is seen from this chart. By using the yield and DFM data obtained from previous products within the same technology, defect densities can be driven from a lower starting point. This methodology has proved invaluable to product engineering to meet required yield targets, even at the early stages of silicon bring-up, regardless of the technology complexity.
This slide provides you with an overview of the range of turnkey capabilities and management services that are offered by GlobalFoundries. The capabilities listed across the top in the gray box include capabilities that we have both internally as well as source externally through third-party partners. Internally, we have capabilities for through silicon via, wafer bumping, and WaferSort, of which I'll get into more detail in the following slides. Through our partners, we also have the ability to source from wafer bump through dropship. Our turnkey services are managed by a dedicated team based in our Singapore facility, close to the Asia hub of operations of many of our partners. And the services they provide include those listed in the orange arrow, from supplier selection qualification through product qualification, inventory management, and planning and logistics. Our objective in offering these services is to provide you with a one-stop solution to getting your product from silicon all the way through the back end in the types of solutions provided below. To enable yield learning on our advanced technologies, we've established wafer bump and sort capabilities in both our Fab 1 and Fab 8 facilities. Fab 1 is operational today with capabilities on tin silver bump, copper pillar bump. For tin silver, we're supporting 140 micron and above pitch. Copper pillar, today we're supporting 110 micron and above pitch, and by its second quarter next year, we'll be supporting finer pitch down to 80 microns. For micro bumping, for TSV and 2.5D interposer applications, today we're relying on our OSAT partners, but it is on our development roadmap to add this capability. Our Fab 8 facility is currently under construction. We'll be installing equipment early this coming year and will be fully operational for both bump and sort there starting in 2015. On the WaferSort side, again, we have extensive capabilities installed in our Fab 1, and we'll be matching those as we bring up Fab 8. Our probe capabilities extend down to the 110 micron pitch to match our wafer bump capabilities. Included on our test floors are real-time yield optimization for rapid feedback to the test floor, as well as the in-house probe card maintenance and repair capabilities. Let's talk a little bit about TSV at this point. First, I'd like to briefly touch on some of the drivers for 2.5D. We're seeing several different areas that are driving the interest in this particular product. The first is yield optimization, where we have customers looking at potentially large monolithic die applications on advanced nodes, and looking at partitioning those devices into two parts as a means to reduce the die size and increasing the yield per wafer, thereby lowering cost. As customers start to look at die partitioning, it also opens up the opportunity to look at functional optimization, where a die could be partitioned by function, and different process nodes or technology nodes could be used depending on the function required. The benefit of this, of course, would be significant reuse of the design without having to resynthesize some of these blocks into the advanced ASIC device, thereby reducing both risk and cost. And then the third area of applications that's driving 2.5D is performance. And in this case, generally, we're looking at integrating memory with logic for increased bandwidth and higher performance per watt. So where are we on our 2.5D efforts? We have established a silicon interposer manufacturing capability to help enable the ecosystem for 2.5D. This facility, this manufacturing capability is installed in our Fab 7 in Singapore. We've have a reference flow in place that has been developed collaboratively with Cadence, Synopsys, and then Mentor Graphics for physical verification. And we've run a number of internal as well as customer demonstration vehicles. The first is the logic memory integration, where we've had several different test vehicles to simulate a GPU or networking type processor with memory devices, as you can see in the upper right-hand corner. Here we're dealing with a full reticle size interposer, a large ASIC die, and a couple of smaller companion die to represent the memories. The supply chain has been fully vetted. We've run materials all the way through our fab, through the assembly flow, and are now in the process of collecting the reliability data. Our projection is we'll be fully production ready for interposer support for these types of products in Q4 of 14. In the lower right, you'll see a logic test vehicle. This was a collaborative effort between GlobalFoundries and Open Silicon. as well as our packaging partner, Amkor Technology. This particular application was designed to take two IP die, in this case 2 ARM core processors, and integrate them on a 2.5D interposer to characterize the electrical performance of such a device. The interposer was 11 by 7 millimeters. Each of the dies were approximately 22 square millimeters, with approximately 1,600 die-to-die signals that were being looked at. The ARM core processors were manufactured using GlobalFoundries 28 nanometer process. The interposer was manufactured in our Singapore 65 nanometer line. This product has been demonstrated recently at the ARMCon conference in December and was awarded the Best of Show. We were able to demonstrate a number of things through this effort, including the full supply chain enablement. We had first time right through the entire process flow, and also the electrical characterization data, which will be published later this quarter. For 3D TSV, the primary market driver here is memory logic integrations, primarily applications processors for the mobile space with wide I/O 2 type memories. We anticipate that the market for this will really start to mature in the late 2015, 2016 timeframe, although we are starting to see some advanced demonstration devices from a few of the suppliers. Our development effort for TSVs in 3D have been focused specifically in our Fab 8 in Malta, New York, in our 20 and 14 nanometer lines. We're using a via middle approach, and we have a number of test vehicles that have been processed and are in process to aid us in our design manual and PDK development. The business model here is similar to what we're using in the 2.5D interposers, where we'll supply full thickness wafers with TSVs to our OSAT partners. The OSATs will then do the backside integration. So today we've completed a number of 20 nanometer as well as a 14 nanometer test vehicle. We've done the TSV integration and characterized the TSV performance, identified the keep out zones, demonstrated the capability to process the wafers through our fab all the way through the back end and packaging. We've collected TSV reliability data at the package level and are ready to look at customer test vehicle tapeouts. Production readiness for 3D TSV, as I mentioned, will be in 2015. This last slide talks a bit about our collaborative supply chain. Again, this is a reinforcement of our Foundry 2.0 model. Our objective is not to become a vertically integrated supplier, but a virtually integrated supplier. We work with a variety of partners, both upstream and downstream of the core GlobalFoundries capabilities, which extend from the reticle manufacturing through wafer probe. On the upstream side, we are working with a number of EDA and IP partners to make sure that the design rules, the design tools are enabled for developing products in our 2.5D and 3D advanced solutions. We work with design partners, and on the downstream side, we're working with key memory partners who will be supplying some of the advanced memories that will be used in these 2.5 and 3D programs to validate that their solutions and our solutions are compatible and can be manufactured reliably. The OSAT partners are a key part of our collaborative development effort in providing us the process development and characterization. So our objective with the collaborative supply chain is to provide our customers with an open and flexible supply chain that provides you options to work with the partners that you're comfortable with. By doing the early enablement with these supply chain partners, we hope to provide you an ecosystem that will ensure a smooth ramp to volume. Thank you.
Thank you for joining us today to learn more about Foundry services from GlobalFoundries. If you have any questions, please post them and we'll get back to you promptly.